The next step that Einstein wants to take is to investigate whether the laws of emission and transformation of light are also of such a nature that they can be interpreted or explained by considering light to consist of such energy quanta. According to the results that we have just obtained, Einstein assumes from these results that when monochromatic light is transformed through photoluminescence into light of a different frequency, both the incident and emitted light consist of energy quanta, which have this magnitude here, R beta nu over n, and nu denotes the relevant frequency of these quanta, and the transformation process is to be interpreted in the following manner. Each incident energy quantum of frequency nu1 is absorbed and it generates by itself, at least at sufficiently low densities of incident energy quanta, a light quantum of frequency nu2. And the principle of conservation of energy requires that the energy of an emitted energy quantum cannot be greater than that of the incident light quantum. It follows that R beta nu2 over n must be less than or equal to R beta nu1 over n. So this is the energy of the quantum that is absorbed, whereas this is the energy of the quantum that is emitted, or if you want, nu2 less than or equal to nu1. Then, Einstein also states that the usual conception that the energy of light is continuously distributed over the space through which it propagates encounters very serious difficulties when one attempts to explain the photoelectric phenomena. However, according to the concept that the incident light consists of energy quanta of magnitude R beta nu over n, one can conceive of the ejection of electrons by light in the following way. Energy quanta penetrate into the surface layer of the body, and their energy is transformed, at least in some portion, in some part, into kinetic energy of electrons. The simplest way to imagine this is that a light quantum delivers its entire energy to a single electron. And Einstein assumes that this is what happens. The possibility should not be excluded, he says, however, that electrons might receive their energy only in part from the light quantum. Then he also assumes that in leaving the body, each electron must perform an amount of work characteristic of the substance. And this amount of work he calls P. The ejected electrons leaving the body with the largest normal velocity will be those that were directly at the surface. And the kinetic energy of such electrons is given by this formula. It is the energy R beta nu over n, which is the absorbed energy, minus the work that the electron has to perform to leave the body. This must also be equal to the charge of the electron, epsilon, multiplied by the potential pi, it's called capital Pi, the potential of the body. If we multiply both sides by the Avogadro's number, we get R beta nu minus P times n, which is called P prime, and then here we have the potential pi, capital Pi, and then Einstein calls the product between n and epsilon, he calls it E, which is the electric charge contained in a mole. Now from here Einstein does some calculations. In particular, he considers P prime equal to 0. He also considers nu equal to 1.03 times 10 to the 15, which corresponds to the limit of the solar spectrum toward the ultraviolet, because remember that we are talking about Hertz. And then he also considers some numbers for E, and we know these constants are beta. And in particular, he uses E equal to 9.6 times 10 to the third power, and he states that pi, capital Pi, times 10 to the minus 8 represents the potential in volts, which the body assumes when irradiated in a vacuum. And by doing the calculation, he obtains that result agrees in order of magnitude with those found by Leonard. According to Leonard, if each energy quantum of the incident light, independently of everything else, delivers its energy to electrons, then the velocity distribution of the ejected electrons will be independent of the intensity of the incident light. On the other hand, the number of electrons leaving the body will, if other conditions are kept constant, be proportional to the intensity of the incident light. And this result is consistent with Einstein's considerations in this article. Einstein saw no contradictions between these conceptions and the properties of the photoelectric effect observed by Leonard. In the previous part, it has been assumed that the energy of at least some of the quanta of the incident light is delivered completely to individual electrons. If one does not make this assumption, one obtains, in place of this equation here, one obtains this one, pi e plus p prime less than or equal to the incident radiation R beta nu, like this. But for fluorescence, for example, which is induced by cathode rays, this is the inverse process to the one discussed previously. So instead of this less than or equal to, we will have a greater than or equal to, because we start from this kind of energy and we emit radiation. But if we start from radiation, the energy of radiation should be greater than or equal to the work that an electron must perform in order to leave the body and the potential energy. Now, concerning the ionization of gases, Einstein assumes that an individual light energy quantum is used for the ionization of an individual gas molecule. From this, it follows immediately that the work of ionization, which is the work theoretically needed for ionization, of a molecule cannot be greater than the energy of an absorbed light quantum capable of producing this effect. So, if we denote by J the theoretical work of ionization per mole, it follows that R beta nu must be greater than or equal to J. And from this, Einstein also makes other calculations showing that his theory here is very close to experimental data of the time. Then Einstein concludes by stating that if every absorbed light energy quantum ionizes a molecule, the following relation must be true between the quantity of absorbed light, which he calls L, and the number of moles of ionized gas J, lowercase j. Lowercase j is equal to L divided by R beta nu, which is the energy of a mole of quanta, and this is the final equation of his paper.